Okay, hello everyone, and welcome to part 1C of sugars and nucleic acids. And today we're going to focus on the properties, reactivity, and the chemistry of sugars. So here's an outline for today's class. We've already covered the first two parts. So like I said, this will be the last portion of this unit. And there's a fair bit of material to go through today. So, if you need to, just take little breaks here and there, but we'll get through it together for sure. Okay, so what are sugars? So sugars are ubiquitous. We know we use them for, to sweeten our food up. We use it in baking. But why are they important from a chemical biology point of view? Well, as I mentioned, we put them in maybe our coffee sometimes, so they're a great source of energy. They are the structural component for the backbone of DNA and RNA of nucleic acids. Okay, so we have the furanose sugars, ribose sugars. So they are the structural unit of nucleic acids like DNA and RNA. They are also important building blocks for proteins. So glycoproteins, a lot of proteins utilize different sugars to help alter its function and its properties. So they can be very important also for proteins. Some other important things about sugars: they're very important in the body for cell-to-cell communication and recognition. So oftentimes a lot of these glycoproteins might be fixed on the outer surface of a cell, and this can be an important signal and an important way for cells to talk and communicate with one another. And there are other differences as well, or other important things about sugars. These are just some of the main ones I just wanted to highlight and talk to you about. Okay, now from a chemical point of view, I'm going to give you two examples of two different molecules here. So on the left here we have a molecule that is a monomer, and directly adjacent to it over here we have another molecule that's a monomer. And the question is, how would we actually put these two molecules together so that they can form this disaccharide? Okay, so this is a disaccharide. And this really comes down to fundamental chemistry. So where are the nucleophiles and where are the electrophiles? As we've seen over and over in this course, in order for these reactions to happen, you need a nucleophile to attack an electrophile. So let's take a closer look at some potential ways in which this could be synthesized. Okay, so here is our new linkage. So you have a carbon, oxygen, carbon. Okay, so in order for this to be made, you have two different ways for this to happen. You can imagine that this is potentially a nucleophile, and then this nucleophile potentially comes and attacks this electrophile. Okay, so this is a potential and here would be a potential electrophile. Now it turns out that this carbon here is not very electrophilic. The main reason is that these hydroxyl groups are really not very good leaving groups. And if we're trying to get the nucleophile to attack, you can imagine there would be issues of regiospecificity. So the other way to do this is to generate our oxocarbenium ion. And recall from the previous unit, we actually, through protonation and proton transfer, we could protonate here and we could form a double bond, and you could get release of water. And this will generate and give you the oxocarbenium ion, which is really a resonance stabilized carbocation. So as I'm showing through resonance here, I have a carbocation that is now positively charged, and they're both valid contributing structures. Now, if this oxocarbenium ion forms, then this is our new electrophilic center. Which is this carbon here. And our nucleophile is therefore this group here. So this is our desired electrophile, and here is our desired nucleophile. Okay, so again, just to recap, potential nucleophile, potential electrophile, they're really not so good, right? You know, but the carbon here is not electrophilic at all. The best way to do this is through an oxocarbenium ion to generate a resonance stabilized carbocation, and then the desired nucleophile can come and eventually attack. Now, from a chemical point of view, you can imagine if you generate an oxocarbenium ion and you get this sugar to come and react, you're going to get a variety of different regioisomers, because how are you going to get the correct hydroxyl group attacking the electrophilic carbon? And furthermore, in order to get this group to leave, you need something to help activate it. So we'll talk more about that when we deal with the chemistry and reactivity of sugars later on during this lecture. Okay, but let's talk about some very simple sugars, and let's talk about glyceraldehyde. And most sugars like glyceraldehyde are chiral. And here's an image of glyceraldehyde. You have an sp3 hybridized carbon with 4 different substituents. And what I would like us to do is to pretend you have your eye in the page here, okay, and you're going to look right through this carbon bond here, okay, and if you do that, you're going to see that you have your aldehyde group pointed away, the CH2OH group here pointed away, and then on the left you're going to have your hydrogen, and on the right you're going to have your hydroxyl group. So this is known as R-glyceraldehyde, and this is the absolute stereochemical configuration. This is known as a Fischer projection, and if you draw it in this format here, it's implied that you have these wedges and dashes in this orientation. A few words about Fischer projections with respect to sugars and how we designate them. It's convention to put the most oxidized carbon at the top. In this case, our most oxidized carbon is the aldehyde. Number 2, the longest carbon chain goes downwards and in the plane of the page. So 1, 2, so here we have 1, 2. So longest carbon chain goes downwards. Vertical bonds point away and horizontal bonds point towards you. Okay, so with that introduction about short sugars, what we're going to do is branch out the sugars. And here you can see you have D-glyceraldehyde, and we have this carbon here, which has this particular stereochemical configuration. This corresponds to D sugars, or D plus glyceraldehyde. If we add an additional carbon and elongate the chain, you can see here that we could have this carbon pointed with the hydroxyl group to the right, or we could have the hydroxyl group to the left. Okay, so here we have 4 carbons. If we keep elongating our chain and splitting them up further, you can see that we're going now to 5 carbons. And if you take those over and add an additional carbon, you now have 6 carbon species. So we're going from 1, 2 compounds, 4 compounds, and now 8 total compounds. And keep in mind that these only correspond to D sugars, in which you can see this carbon here, the stereochemistry is fixed. If this were inverted, these would correspond to L sugars. I do not expect you to memorize this table whatsoever, but it just gives you an appreciation of the complexity and different types of sugars that we have, especially when we start hitting 5 or 6 carbon sugars. So a couple sugars that we will probably spend more time on than other sugars are things like ribose, glucose, mannose, galactose, and maybe a little bit of talose. Okay, let's talk a little bit about the chemistry of sugars. So aldehyde groups can be readily oxidized, and if we take our aldehyde group and we can do something called a tolerance test. Essentially what happens is that if you take silver in its +1 charge, what's going to happen is that the silver will now become elemental silver, and you'll get this like silver mirror forming in the glassware. So it's a great way to see whether you have a sugar that has an aldehyde group, because the aldehyde can be easily oxidized. So this is also known as reducing sugars. So aldehydes can be oxidized, but aldehydes can also be reduced. Okay, so if you have an aldehyde in this orientation here, you can imagine instead of oxidation, you would have a hydride anion coming and attacking that aldehyde to generate now a fully reduced form, to generate an alcohol. And in addition to oxidation and reduction, they can react with a nucleophile. And you can really think of reduction as reaction with a nucleophile. The hydride is really the smallest nucleophile around that can do so. However, if you want to think sort of more clearly in terms of what practical reagents you could use, you could think of something like methyl magnesium bromide, a Grignard reagent, which could be used as a source of something like -CH3, and this could be used to attack the aldehyde to generate now this new species here with now a carbon off of it. All right, so that's what sugars are quite good at. And if we think of the reactivity of sugars in terms of how they can accept electrophiles, and if we think to the prebiotic synthesis that we were talking about earlier in this unit, and also with peptides and proteins, our very good friend here, the cyanide anion, is a ubiquitous molecule that is around. So if you think of having glyceraldehyde or some very small carbohydrate around, you could easily imagine that if we want to elongate our carbohydrates naturally and add 1 carbon at a time, the cyanide anion would be a great example and a great way to do so. So you can imagine the cyanide attacking that aldehyde. Now you have these new carbon-carbon bonds, and you get a mixture of stereoisomers. So if we had very simple sugar at the beginning prebiotically, get a mixture of stereoisomers, and then you could imagine you could hydrolyze those nitro groups to carboxylic acids, and you could generate a class of carbohydrates, perhaps known as aldonic acids. And then there must be some sort of mechanism to reduce carboxylic acids to aldehydes. And in lab, we know of very good reducing agents like sodium borohydride, for example. But one class of molecules that we talked about last time in our last unit was something like NADH, right? We learned how that could be a natural source of reducing agent. We saw how it could potentially be formed prebiotically. So you could think of this NADH acting as a hydride source to the aldehyde or to the carboxylic acid to generate the aldehydes. And then from here, you could recycle and go over this again. So you can now go from a 4-carbon species, add additional carbons to generate 5-carbon species, so on and so forth. So perhaps some type of mechanism like this was a way to generate complex sugars prebiotically. Some other things about sugars, and I'll probably come back to this slide in a little bit, is that carbohydrates are typically not observed in their linear form, but often form in cyclic forms naturally. Okay, so we've seen that chart where you can have 4, 5, 6, you could even have 7 carbon containing sugars, and they're all drawn in a linear form. However, naturally, what tends to happen is that you have a sugar, and I'll just draw glucose here. And glucose here in its form, linear form, will actually come and undergo an attack from this hydroxyl group here to form a 1, 2, 3, 4, 5, 6-membered ring. Okay, so after proton transfer, you're going to generate a molecule here that forms a stable chair conformation. Okay, so if we actually number and label the carbons, this is 1, 2, 3, 4, 5, 6. This corresponds to carbon 1, 2, 3, 4, 5, and 6. You can imagine that this nucleophile could attack this aldehyde either from the top or from the bottom. So if that were the case, you actually would generate another stereoisomer in which you'd have this OH group in the different orientation. So these are both diastereomers, stereoisomers of one another. And this hydroxyl group here is in this upward motion. We call this the beta anomer. So therefore this is called glucose. This group here is the alpha anomer. We call this alpha glucose. Okay, anomers. I just use the term anomer. So what is an anomer? An anomer are stereoisomers at this anomeric carbon position. Okay, and I'll talk about anomers in just a little bit when we talk about the anomeric effect. Stereoisomers at the anomeric Okay, so these are anomers. What this little chart here is highlighting and showing you is that if you have some type of aldehyde or ketone, depending on what the R group is, and you want to form some type of acetal or hemiacetal, the rate constant and the way that this reaction works is really going to be dependent on what you have as your R groups. Okay, so if you have something like acetone, for example, you're going to have a pretty low equilibrium constant. But as soon as you start making this more electrophilic, things like acetaldehyde, formaldehyde, you can see the rate constant dramatically increases. For this one here, where you have two trifluoro groups, you can see the rate constant dramatically increases due to inductive effects from the fluorine. Okay, so so this just sort of gives you an appreciation of how well acetals, hemiacetals can form depending on what their substituents are. In this case here with sugars, It's an aldehyde, so you might say, okay, the K equilibrium might be around 1. However, in solution, if you mix this with water, you actually get like a 99%, greater than 99% of the sugar will actually adopt the cyclic sugar form. And this is, due to a number of effects, but the main one being that glucose forms a 6-membered ring because you form the stable chair conformation, and the substituents are all equatorial, and we avoid these 1,3 diaxial interactions. So it's a very, very favorable structure from a stereochemical point of view. Now, not all sugars will form 6-membered rings. We can also get 5-membered rings forming, right? As we've learned with ribose and other 5-membered rings. So for furanoses, we can actually get intramolecular attack from carbon number 4. So 1, 2, 3, 4. This attacks here, and you can find a ribofuranose, 5-membered ring. And ribose, for example, prefers a 5-membered ring as opposed to 6. Otherwise, there would be an axial OH in the 6-membered ring. So nature has picked whatever is more stable and more energetically favorable. And it just so happens for ribose, 5-membered rings form. For glucose, 6-membered rings form. And it really just comes down to the geometry and making the best looking structure for that molecule. And 5 and 6-membered rings, as you know, are very favorable in organic synthesis and for any type of ring compound. Okay, why do we get cyclic acetals of sugar? So I mentioned, okay, you can get that 6-membered chair formation occurring, but from a thermodynamic enthalpic point of view, let's think about this a little bit. Okay, so number one, when you're doing this reaction, you're exchanging a pi bond for a stronger carbon-oxygen sigma bond. So pi bonds are not as strong as sigma bonds. So if you can get a stronger bond, that's more energetically favorable. Okay, exchange for a pi bond for a stronger carbon-oxygen sigma bond. During this reaction, the delta S remains about the same. You do get some penalty a little bit because you're getting, in this example down here, you're getting 3 molecules coming in to form this acetal, 2 molecules out. That's entropically unfavorable. For sugars, you have 1 molecule you're starting with, and when you form that cyclic molecule, it's still 1 molecule. So the entropy is not increasing, but it's not horrible. And then furthermore, little ring strain. And if you compare this example here, and on the previous slide we showed that the equilibrium constant for that is 1, because you have an entropic penalty from 3 to 2, which, however, with glucose, the delta S remains about the same. So that K equilibrium is actually going to be much, much higher. So in terms of free energies, or delta G equals to delta H minus T delta S, you can see that your enthalpy is actually really quite good because of the stronger carbon-oxygen sigma bond. And the enthalpic penalty, it's not good, but it's okay, it's not bad. So the enthalpy wins out, and that's why we get that happening. Okay, so we talked a little bit about anomers, and let's talk a little more about anomers. Okay, so let's draw the 2 main anomers of glucose. Okay, so there's a chair form of alpha glucose, and if you want to look at the beta form, it's going to look just like this, except you're going to have your OH in that orientation. Okay, So nucleocene are during hemiacetal formation. So we went through that a couple slides ago. These are called anomers, beta hydroxyl group up, alpha OH group down. Stereoisomers at C1, they are diastereomers. So all anomers are diastereomers. All diastereomers are stereoisomers. Okay, but not all stereoisomers are diastereomers, and not all diastereomers are anomers. So that's sort of some fun facts. Alpha and beta anomers of glucose can be crystallized in both pure forms. So you can actually crystallize these out and have therefore separate containers of alpha glucose and beta glucose. However, if you take and crystallize these molecules and place them in water, you get something called Muta Rotation. Okay, so in solution, Muta Rotation occurs. Okay, so what is Muta Rotation? So in solution, if you take beta D-glucopyranose, which is the same as beta D-glucose, and if you measure its optical density in solution, it's going to rotate at around 19 degrees. If you take alpha D-glucopyranose, which is alpha D-glucose, this will have a different optical density at around 112 degrees. Okay, so I'm going to come back to the slide because I want to show you what happens if you put these in solution. So in solution with catalytic acid present, just something to transfer protons, you get something called Muta Rotation. So what is Muta Rotation? All right, so let's, what we're going to do is we're going to plot our optical density as a function of time for both of these molecules, and look what happens as a function of time. All right, so this is going to be our alpha glucose, and let me just flip back. The y coordinate for that is 112 degrees, so let's just write that in, 112 degrees. And then recall our beta one was 19 degrees, and that looks like this. Okay, so you put these in solution with water, and you just need even just water by itself is enough to catalyze this. So you take tap water, which typically has a pH of around 6, or can fluctuate, will definitely catalyze this reaction. If you measure the optical density of both of these solutions as a function of time, this is what you'll notice. You'll notice that beta glucose, starting with an optical density of 19 degrees, will actually start to increase as a function of time. And it's going to sort of level off and plateau off like this. In contrast, the alpha one will actually lower its optical density as a function of time, and it will actually converge with the same sample, the same beta sample. And if you actually measure this, this will actually turn out to be 53 degrees. And then if I just add some dotted lines here and kind of match up, I could write 53 degrees right there. Okay, so they all converge to the same equation. Now, let's see what's happening. So if we take a look at the difference, the change, the delta alpha optical density between when we start the experiment to when we end, we can see here we've gone from 112 to 53, and we'll call that delta alpha degree, superscript degree. If we do the other one, this will be alpha beta superscript degree, and we can see that the change here is quite, is also significant. So the change between 112 and 53, this is equal to 59 degrees. and the change between 53 and 19, this is equal to 34 degrees. Okay, so what's happened is that they've undergone some type of Muta rotation, and let's calculate the percentage of, let's start with beta glucose once it equilibrates. So that's going to be equal to the change in alpha beta, the change in delta beta plus the change in delta alpha minus the change in beta. Okay, so if we do that, we're going to get 93 minus 34 divided by 93. That's going to be equal to around 63%. Okay. If we look at alpha and we apply the same formula, we take, we look at the whole sum of the change in beta and alpha over the change of alpha and beta minus just the change in alpha. That will be 93 minus 59 over 93, and that will be equal to 37%. So it looks like our beta anomer is now, instead of being 100%, is now 63%, and our alpha anomer, which started 100%, is now 37%. So the beta one is in excess, and you might say, well, it kind of makes sense because this OH group is equatorial, whereas over here it is axial. Okay, so before we talk about these percentages and what was predicted, let's go back to this Muta rotation slide and try to understand mechanistically what happens in the environment. Okay, so how do we go from beta D-glucose to alpha D-glucose? So, as I mentioned, you need to have some catalytic protons present. So let's draw protonated water, great proton source here. And in order to open up this bond here, you can imagine that we're going to get electron donation coming down, and then we're going to pick up a proton as this carbon-oxygen bond breaks. And then you can imagine that after proton transfer, that this bond here is now free to rotate. It's free to rotate. You can now have your pi bond oriented in a different position, and then you can now get a tack occurring at this carbonyl group, as I'm showing here, and this would give you the different anomer. Okay, and of course you need to do a proton transfer. So these are very fluid movements, and these are all reversible. So you can start also with alpha D-glucose. This can come back down, and then this can pick up a proton, as we've seen like in our first example, and you can go back and forth. So equilibrium just keeps going until there's a steady state of both of them. And as we've learned, alpha D-glucose will be abundant in around 33%, 34%, and this one here will be around this one will be in around 37% once it equilibrates, and this one will be around 63% once it equilibrates. Now, here's the interesting thing, is that if you actually use some predictive models, I'm going to slide back here and predict what the calculated percentage would be based on computation. It turns out that the alpha glucose anomer is expected to be abundant at around 11%. Okay, this is predicted computational. Okay, and this really largely just takes into account sterics. Okay, so you know that axial is not as good as equatorial from a steric point of view. And in contrast, the beta glucose was expected to be around 89%. Predicted computational value. Okay, but from the experiment that we just did, you can see that the numbers are actually quite different, right? So the experiment numbers show that you actually have 63% and 37%. Okay, so that's actually a big deal. You know, 11% versus 37%, that's more than 3 times the estimated value. So there must be something else going on that is accounting for this difference. Okay, and I'll explain that to you in a second. Before we do that, I just want to, this slide is from the textbook. It really just shows how you can have, you know, ring opening and closing under acidic and basic conditions. Okay, so this is for any type of 6-membered ring. Ring size, as I mentioned, 4 and 5-membered rings are favorable. So you get a large percentage of them closed, whereas if you have 4-membered rings, those are typically too strained. So it's not often that you see 4-membered rings or larger than 6. Okay, so, you know, heptagons, octagons are actually really not the best from a geometrical point of view. 5 and 6 are the best. And here, this is just showing that, you know, glucofuranose, which is glucose in a 5-membered ring, is just not as favorable compared to glucopyranose, which is in a 6-membered ring. Because in theory, if you take glucose, you could form a 5-membered ring, 6-membered ring, or even a 7-membered ring. Okay, the 6-membered ring by far wins that battle. Okay, but let's describe why that alpha anomer is so high compared to, in percentage, right? It was 37% versus 11%, which was predicted. So the anomeric effect describes why the alpha anomer population is much higher than predicted. Okay, so a couple things to talk about here. One is, if you look at panel A, you can see that we have this carbon-oxygen bond here, and then we have another carbon-oxygen bond here in the sort of this alpha position. If you actually measure the bond angles, this carbon-oxygen bond here is actually a bit shorter than this one. And you might say, well, why would that be? Because they should be relatively equivalent. So a good way to explain this is to actually draw the sigma star orbital which is actually empty. And what is postulated to happen is that you actually get stabilization of that carbon-oxygen sigma star bond from the p electrons on the oxygen. Okay, so it's almost like double bond character, but because you can get donation into here, that will shorten that bond a little bit and make that a little more stable. Okay, and this has to occur in what we call an antiperiplanar orientation. Okay, so if I draw sort of an analogous type of species, and I'm kind of showing that sigma star orbital, you can get donation occurring in that orientation, just like I'm showing over here on the left. However, if you have the beta anomer, your sigma star bond will now be facing this way, and no matter how you try, you cannot get overlap coming down into something that is antiperiplanar to that carbon-oxygen bond. Okay, so you're not going to get electron donation and stabilization. So you cannot get overlap. When the carbon-oxygen sigma star orbital is in the beta orientation. Okay, so that's kind of interesting. That makes sense in terms of why maybe the anomeric effect, or why the alpha anomer is, more than 3 times in population compared to predictive models. Some other interesting experimental evidence suggests that if you have a molecule like this, where you have an O R group substituent in the beta format, and if this were to leave to form an oxonium ion or an oxocarbenium ion, a carbocation that's resonance stabilized, this is actually much slower when it's in the beta orientation. Whereas if you have this in the alpha orientation, it's actually much faster. And it's much faster because if you're getting electron donation to that sigma star orbital, it's much easier for this leaving group to leave. So you've already, in some ways, initiated that process by stabilizing it in that orientation. So it's much faster, whereas here it's much slower. So those are some other examples to show. So that's sort of one main fact from the anomeric effect. Another interesting sort of secondary way to explain this will be illustrated here, where you have the alpha and the beta anomers, beta, alpha, and I'll draw the non-bonding electrons on both of these. Okay, so with the case of beta, if we were to look at the dipoles, you can see that we have dipoles that are aligned. Okay, so there's always some, some movement of the electrons going this way and giving those dipoles. If you look at the alpha, you have dipole going through that oxygen, and over here you have the dipole actually going the other way. So in terms of a stability point of view, alpha, if the dipoles are canceled out, it's actually a little bit better. Okay, whereas if dipoles are aligned, you get some electronic repulsion, and that's a little bit unfavorable. So this is also why the alpha anomer is formed in 37% versus 11%. Dipoles here are, they're canceled in some ways, right? They're opposing, so more stable. Okay, so those are some interesting features of the anomeric effect with respect to anomers and stereochemistry. Now, the way that we draw sugars is, here's your glucose molecule, and this is the linear form. I'm just going to draw on those hydrogens. So this is like our Fischer projection. If you actually take this molecule and flip it on its side, and then rotate the molecule, you now can see that you get this hydroxyl group attacking this aldehyde here to give you this molecule here, right, which is your glucose molecule. This is also known as a Hayworth projection. You can have beta where it's up, alpha where it's down. It's different from the chair, in which this is sort of really based on the Fischer projection and turning it on its side. Similarly, you can also have a Hayworth projection of ribose. It's not a true representation of what this molecule looks like in three-dimensional structure, right? As you know, glucose forms a six-membered ring formation, and this is a better representation of what that looks like. Whereas a Hayworth is more for cartoon drawing and more for sort of a superficial representation. Ribose, again, is not a flat structure like this. It actually adopts something called sugar puckers, in which some of the different carbon bonds flip out in different orientations in order to accommodate the best energetic structure. And for those of you who might be taking the advanced topics next term with me, we'll definitely talk more about that in the winter. Okay, now let's talk about some chemistry of sugars. So we talked about projections, stereochemistry, and at the beginning of this lecture, we were really interested in how we could get these two molecules to react with one another. And as you can imagine, it's going to require a lot of different protecting groups. So reactions of sugars. So we're going to learn some new protecting groups. But one thing that we need to do is we need to really find a good way to protect all these different OH groups of glucose, or any sugars for that matter. So if we actually take something called acetic anhydride, often abbreviated as AC2O, acetic anhydride, and react this with some kind of base like triethylamine, you can actually get a sterification at all those OH groups. So what you'll end up having is now acetyl groups at each of those positions. This reaction works really well. Acetic anhydride is it's very reactive. You can add triethylamine, or you can even add some other bases to help catalyze that reaction. It's super stable, and it's also very inexpensive, and it's relatively safe. So you get, global esterification. So you can draw it like this, but we also like to use the abbreviation AC. It just makes things a lot simpler. So you'll often see acetyl group drawn like that. Okay, another great way to protect the OH groups is to use ethers. So if you take, again, let's draw glucose. If we take glucose and react this with something called benzyl bromide, this is abbreviated as BN, BR, and you add some type of base, you will get complete coverage and benzylation at all those groups. Okay, and the abbreviation for benzyl is BN, as I just mentioned, so your product will look like this. Okay, so two different protecting groups. Suppose you want to create an ether, so this will be kind of ethers continuation, but you want to only protect one of them. Okay, so here's a ribose type molecule. You can actually treat this with a big bulky group. So in the previous example, we used benzyl bromide, which is relatively small and pretty electrophilic. But if you treat this with one equivalent of triphenyl carbobromide, this will react via SN1, and this group here, being a primary hydroxyl group, will preferentially react exclusively first because it's a better nucleophile. It's less sterically cumbersome, and if you control the equivalence, then you don't really need to worry about reacting this big bulky group. So this is often abbreviated as trityl group, as I'm showing here. Selective steric hindrance, only the primary reacts. I'll say only the primary alcohol reacts in the presence of other alcohol groups. Another really great protecting group is the acetyl protecting group. So you could take this group molecule that you've made, and then you could treat this with acetone and catalytic acid. In this case, we're using para-toluene sulfonic acid, which looks like this. And what this will do with acetone, this will actually generate something called the Isopropyllidine group. I encourage you to think about the mechanism in terms of how that would actually happen in the presence of acetone and the acid. And again, just think back to basics in terms of what your nucleophile and electrophile will be at each step. It's a very nice protecting group. It's a stable 5-membered group. Okay, and so let's go through an actual synthesis of a very classic molecule that has been around for a while. So, okay, so make AZT from deoxythymidine. So what is AZT? So AZT is the structure here. So it's an azetothymidine compound. It's been around for a very long time, and it's still used somewhat, but it's used predominantly as an antiviral medication or anti-cancer. And, you know, it's a good time to talk about this because we live now during this COVID-19 pandemic. AZT is, if you think back to the mechanism of enzymatic synthesis of DNA or RNA using the polymerases from the last unit, you need to have like the OH group on the 3' position. That's necessary for elongation, right? So you kind of build it off of this OH group, which will react with triphosphate, so on and so forth. So the AZT group, what you can see here is it looks very much like a regular nucleoside. However, it can't elongate. So what happens is that you get chain termination, and you essentially poison the polymerases, and therefore replication would not be able to occur. This is it's a fairly harsh drug. It's not very specific. So as I mentioned before, it's used often, well, not often, but it's used for rapidly dividing cells like cancer cells, or maybe even some antiviral medications. All right, so make AZT from deoxythymidine. So let's think about how we could generate this from deoxythymidine, which is actually readily available. You can buy this commercially. And let's think about the different protecting groups of how we could generate this azide. All right, so what we need to do is we need to protect this hydroxyl group and not really touch this at the moment. So we can just use that strategy that we just learned about using the trityl chloride. So now we have that trityl group on that primary hydroxyl group. And at this stage here, what we need to do is we need to add an azide molecule here. There's a couple of different ways to do this. I'm going to show you sort of the more classical way that this has been done. And in some pharmaceutical companies actually still use this method. So this is the desired electrophilic site. So a good way to add an azide is to add the azide anion, N3-, and that looks like Looks like that. So it's actually pretty good nucleophile. So if this were to come here and react, one of the problems is that the OH is actually not a good electrophile or not a good leaving group. So what we're going to do is we're going to convert this hydroxyl group to something that's actually a very good leaving group. And we're going to use something called methane sulfonyl chloride or mesyl chloride. And what's going to happen is that this OH group is going to react here. We're going to add some base triethylamine, and you're going to get release of the chloride. And after proton transfer, what you're going to now have is you're going to have this methyl sulfone group here. And you can see here that this is actually now a good leaving group because you have the ability, I won't draw it in, but you can just follow the tip of my pen here. You have the ability to move electrons here and into this oxygen. In addition, you can move electrons here and into that oxygen. So this is actually a really good leaving group. Okay, so you might say, okay, great. Now let's add our azide, and you could add something like lithium azide or sodium azide. It's just the counter ion. These come, you can purchase these as salts. And if you do this reaction, what are we going to get? So N3 minus, here you have a good electrophilic spot. If this comes in, this is going to come and react, and you're going to remove that. The mechanism by which this does this is SN2. So what's going to happen to the stereochemistry of that carbon? Well, you remember that you get inversion of stereochemistry. So in fact, if you do this reaction, you're going to generate the azide group coming towards you now in a different orientation. And you might say, well, is that important? Absolutely. This molecule here, after you deprotect the trityl group, it won't work. It won't fit in the polymerase active site, so it won't be an effective strategy to target polymerases. So we need to have the azide pointing away from us. So how would we do that? Well, I'll just tell you because we're doing this pre-recorded, but if you take this molecule here, and let's say we add sodium hydroxide, an aqueous solution, heat this up to 100 degrees, your hydroxide is now a good nucleophile. This will react here, displacing off this good leaving group, and you're going to get the hydroxyl group pointed in this orientation here. And you might say, well, that really didn't accomplish much. Well, it did, because what you've done is you've inverted the stereochemistry substituent at this position here with OH. And now what you can do is you can add your mesyl chloride and then add your lithium azide to get the desired stereochemistry. And then the trityl group, think back to proteins and peptides, we're going to need to deprotect that through resonance stabilized carbocation. So we're going to use weak acid to remove that. So this will be a three-step process. Mesyl chloride, triethylamine, lithium or sodium azide, and then 5% TFA. Okay, so that's how you can generate AZT. Some protecting groups and some overall strategies to do this. It's really important when you're designing and synthesizing sugars that you really think of the stereochemistry, because one change in stereochemistry can really impact its bioactivity, might not work, for example. Here's just an example showing that, if you're designing sugars, disaccharides, trisaccharides, and you think of how to couple them together, there's so many different ways to put them together. Even if you have the correct nucleophile and electrophile, you have to think of whether you get the right stereochemistry, because you could imagine forming an oxonium ion here. This could get attacked from the top or from the bottom. So as organic chemists, we really have to think a lot about this, because in solution, these molecules rotate freely and they don't really have necessarily a preferential bias. However, nature does this all the time, and the molecules are held in place by enzymes, and these are extremely efficient, and they're very, very regiospecific. Okay, so the selectivity of the anomer formation in glycosides. Okay, so as I just mentioned, the oxonium ion can be attacked from both the bottom and top face. So this is often denoted as ray and C faces to give a mixture of anomers. So, so how do we control that? All right, so there actually is a really good method to do this. So if you take your glucose and hyperacetylate it, like we've done before, so you could use triethylamine or some other trisubstituted base, you know that you will generate this compound here. Okay, so what we're going to do is we're going to treat this compound with HBr, hydrobromic acid. And what HBr will do is this will pass a proton on to the oxygen of this acetyl group at this position here. So that becomes protonated, and is actually a pretty good leaving group now. Okay, so as you can imagine, now we can form our oxocarbenium ion. This will leave as acetic acid. So what we will have is this oxocarbenium ion like this. Now you have a bromide anion solution that's come off after that initial HBr attack. The Br minus will come and attack, and you might say, okay, it can attack from the alpha side or the beta side. However, during this reaction, we get exclusively, or pretty much just, the alpha anomer. Okay, now I want you to think why that is. Why don't we get attack occurring from the beta side? Why does it only occur from the alpha side? So if we're using a glycosyl halide, like a bromine group, think of the anomeric effect, right? Think of electronegativity. So halogens, like Br and Cl, those are very electronegative, right? So they're seeking electron density. They really want electron density. So you're getting a much stronger anomeric effect when you're using something more electronegative like a bromine compared to like an oxygen. So you get a greater pull from these oxygen electrons here in stabilizing the carbon-bromine sigma star bond. Okay, so I'll just write down only the alpha anomer is formed with glycosyl halides. All right. And then what we can do is we can use this we can use this glycosyl halide to our advantage. So taking the molecule that we just generated, if we treat this with methanol and silver carbonate, the silver actually in solution will have some type of interaction with the Br, and it's really going to want to come out and precipitate as silver bromide in solution. And it's not going to happen by itself. It's really going to be promoted by oxocarbenium ion formation. Okay, so this will get back off, this will form, and what happens is that at this stage here, we now have this group here. Now you might say, okay, methanol could come and react. Certainly. Now, the acetyl group in this position, I've drawn it out, and it is actually a protecting group. But what I'm showing you here is that the acetyl group is actually on its own participating and reacting here to form an oxocarbenium ion. It's forming a cis-fused dioxylenium ion, and it can only attack from the bottom. So I'm just going to redraw this because it's a little bit messy. Okay, so here's our oxonium ion or oxocarbenium ion. Okay, so what's going to happen is that this pi bond will come and react, okay, to form this here. So this is your cis-fused dioxylenium ion, and it can only attack at alpha because of the geometry. It's actually a stable 5-membered ring, but it's a really great way to trap a carbocation. And then later, the methanol can come in and it can attack only from the top because this is already occupied from the alpha position. Okay? So when the methanol attacks, you generate a beta glycoside. So you can imagine using and applying this not for things like just methanol, but other sugars that have OH groups. And you could force and make beta glycosides exclusively and not necessarily make a mixture. Okay, so we'll definitely talk more about this and have some more practice investigating and looking at this chemistry. So what I'd like to do is just take a couple moments and just summarize some of the protecting groups that we've seen today. Okay, so let's see. Let's look at the name, structure, the uses, the deprotection, and how to install it, the installation. Okay, so the first one we looked at was the acetyl group. That looks like this. Uses, all alcohols. It's also useful for, you could even use it for amines. Talk about deprotection in just a little bit. In order to install this, you can use things like acetic anhydride with base or acetyl chloride and base. That works well. Trityl. Right, that's the triphenyl methyl group. This is, you can in theory use it for alcohols, but it really works best for primary alcohols. Installation, trityl chloride, with base, like a tri-substituted base. Benzyl group looks like this. Great for all alcohols. Again, benzyl chloride or benzyl bromide with base, we'll install that. And then we looked at the isopropyllidine. Very briefly, but that's the structure here in which it works really well only when you have the two hydroxyl groups that are cis and on the same side to each other, and they have to be adjacent. So imagine if you had one of the hydroxyl groups pointing up, then this system would not work. And the installation, you use something like acetone and catalytic acid, often things like para-toluene sulfonic acid. For deprotection, let's talk about isopropyllidine. So you're actually taking the acetone and forming like an acetal. So in order to do the reverse reaction, we need to simply add water and undergo the reverse set of reactions. So strong acid, like sulfuric acid with water. Benzyl groups. A great way to remove it is to use things like HBr or H2 over PDC. So you can just simply do a hydrogenation and release off toluene and your alcohol. Trityl group, we've seen that already. 5% TFA or 5% trichloroacetic acid. Emphasis again is that these are weak acids. Then finally, deprotection of acetyl groups. You can use something like ammonia, right? So ammonia will come in, attack, and then release off the alcohol. You can use sort of a weaker base like potassium carbonate, or even something like sodium hydroxide. Okay, so I just want to highlight some naturally occurring di and oligosaccharides. Again, I wouldn't, I would expect you to understand the beta glycoside linkage between these units, but I wouldn't say, oh, draw maltose from memory. Okay, so maltose is 2 units of glucose, okay, and it's held together through a 1,4 linkage, okay, and this is what maltose looks like. Lactose, which is sugar coming from milk, this is actually formed through a beta glycoside, not an alpha, okay, so here's your beta glycoside, and it's a 1,4 linkage, okay, and it's not 2 units of glucose, it's actually 1 unit of galactose, 1 unit of glucose. So an enzyme that some of us have, lactase, actually takes milk sugars and breaks it down. And inevitably, some people are lactose intolerant and have trouble breaking down this structure, and then this can cause stress on the digestive system. Sucrose is table sugar. This is the stuff that you use to bake and that tastes really good. It's formed between glucose and fructofuranose, and it's an alpha 1,2 glycosidic bond, as you can see here, okay? Table sugar. And in addition to disaccharides, blood cells have very complex polymers of different glycosidic units. And here's an example of an oligosaccharide showing a combination of alpha 1,4 glycosidic bonds in addition to branched alpha 1,6 glycosidic bonds. So you can think that there's really a lot of different ways and combinations to make different types of oligosaccharides just based on how these bonds are formed. That's why they're used for like cell recognition, and they're quite, like a small change in stereochemistry can really affect its structure and hence function. Okay, the last slide, or the last thing, or a couple last things I just want to tell you about is sugars in the chemical industry. All right, so sugars in the chemical industry. So let me just get another piece of paper. All right, so sucrose, as you know, is what some of us might add to our baked goods or coffee. But sucrose, if you don't use those carbons, what can happen is that they can be used as fats, or they can be converted to fat, and then, you know, if you're not using that energy, then individuals can have issues with weight and obesity, so on and so forth. So there's a lot of interest in the chemical industry to design molecules that actually taste good, but maybe are not metabolized. One molecule that you have seen before is something that's actually not a sugar, but is actually like a dipeptide. And this molecule here is a dipeptide with a methyl ester. It's called aspartame. And aspartame is found in things like Diet Coke, and other, in other drinks. And some people like it, but for others, some people think it has sort of a bad taste. It doesn't really taste like sugar, and you can't really bake with it either. So it's not stable to heat or pH. So you won't find this in, cakes or cookies. So it's typically just added to drinks. And furthermore, some patients who might have a rare disease called phenylketonuria, they have trouble metabolizing this because they need to have a diet that's restrictive in the amino acid phenylalanine. Okay, so there's a molecule here that looks like sucrose. So I'm just going to draw it out. Okay, so here is sucrose. And there's a kind of an interesting story behind this. So some insects are also attracted to sucrose because they use that as their primary energy source. So if you have, maybe issues with ants in your home, some ants and bees are attracted to sucrose. So I think at King's College in the 1970s, there was a professor, and he was working with a postdoc, and they were trying to design a new class of insecticides, something that, an ant or a wasp or something might ingest, but it would be toxic to them. So what they were doing was they were taking these types of molecules and they were chlorinating them and doing a bunch of different transformations. So essentially what they were doing was through a variety of steps, and I'll show you what those are in a little bit. They were taking molecules like sucrose, and sucrose was relatively cheap, so they could use that, and they were chlorinating at specific positions. Just bear with me, I just want to make sure my structure is correct as I draw it. Okay, so they really took this molecule, they did some things like adding protecting groups so they could use things like acetic anhydride. Then they use things like PCl5 or POCl3 to chlorinate. And then they would do like a deprotection, maybe with like ammonia or something. But the point is that they have a molecule here that looks like sucrose, right? Except they have 3 chlorine atoms installed. Okay, so once this postdoc made it, he had just recently come from India, and the supervisor said, I want you to take these compounds and I want you to test them, okay? And he interpreted that as, I want you to taste them. So he actually took this compound, put some on his tongue, and to his great surprise, they were actually really, really sweet. They're in fact, 1,000 times, after doing more tests, they're actually 1,000 times sweeter than sucrose. And later on through studies, they noted that they get increase in sweetness because it's a more hydrophobic compound, so it actually gets absorbed by the taste buds better. But this compound here is not subject to metabolism, so you get the benefits of this compound through something that's sweet, but it's simply excreted out. And it's been shown that it's actually been quite safe. Now, do I recommend people tasting the chemicals that they make? No. This was sort of perhaps a little bit of a freak accident that turned out into a happy story. This compound here, so as I mentioned, is 1,000 times sweeter than sucrose, and you very likely you have used it or seen it before in everyday life. So this compound here is called Splenda. So if you go to your local Starbucks, you'll find packets of Splenda. You might even add that to your coffee. So it tastes great, but that's exactly what the structure is. Makes you think a little bit twice, right? Whether you want to ingest a halogenated hydrocarbon instead of the real thing. Anyways, just some food for thought. Okay, so I think we are at our last slide, which is a conclusion slide. And so this part 1 has been divided over 3 parts. So there's a lot of information here, but just to kind of recap, part 1 dealt with the nitrogenous bases. We kind of looked at the properties. So the nitrogenous bases are actually aromatic and stable, and these come from things like DNA and RNA. Number 2, part 2, we kind of talked a lot about different things. The main take home from that was that heterocyclic components of DNA and other related molecules may have formed prebiotically by using very simple molecules. By single molecules such as hydrogen cyanide. Okay, remember it did 4 things: base, acid, could act as a nucleophile, electrophile. And then finally, this unit's been a little longer than I normally like to record, but there's a lot of good information here, and I had trouble sort of thinking about splitting it up. So I did it all in one shot. A lot of different things. Definitely the chemistry of sugars is complex and requires multiple protecting group strategies. Okay, so with that, this concludes part 1 of sugars and nucleic acids. See you next time.